In the second part of 7.3, we are going to use the strategies of solving exponential equations in exponential application problems. A few of the kind of application problems that we are going to talk about. We're going to deal with population growth and decay. And population growth can be like the population of a city or a town or a country, either growing or decaying. But population growth could also be something like bacteria or a certain substance that is growing or decaying exponentially. We also are going to look at things like interest and investments. So money type questions where we have a repeated multiplication of an interest rate over and over again, then that results in an exponential equation for that. And also when we are looking at value of items and either values that appreciate or values of items that depreciate. So something that would appreciate, maybe like real estate or a house, that value that appreciates over time. And then something that depreciates would be like the value of a car. So these are the kinds of application problems that we are going to look at in this section. And the one equation that we need to remember is this right here. Y equals A times B to the T over P. This is our basic form of an exponential equation for an application question. It is on your formula sheet, so you don't have to memorize it, but we're going to use it enough in the next few questions that you should know it. Let's talk first about what those letters represent. Starting with A. So A, which is our coefficient here in front of the B, actually represents the initial amount. So if we're talking about the population of, let's say, a city, the population initially is our A value. If we're talking about an amount of a substance that's decaying, that amount at the beginning is our initial amount. It's our A value. If we're talking about an investment question, the initial amount of money invested would be your A value, and the initial value of the object would be your A value. So the initial amount, it is the amount at the start of the problem. B is our base. So B is going to be our growth factor. So with B, we're going to look for words like doubling or tripling or half-life. All of those words lend itself to what the base is going to be. Doubling would let you know that the base is 2. Tripling would let you know the base is 3. Half-life tells you that the base is 1/2. Sometimes the growth factor is a percentage, so especially for those interest questions and the value of objects, usually what happens is the value appreciates or depreciates by a percentage. And so when you're given it as a percentage, you have to be aware that we're going to take the percentage, we're going to convert it to a decimal, and then we're going to be really careful about how we put that base in. Just like with basic exponential functions, because B is our base, it's going to show or reflect whether we have exponential growth or exponential decay. If your base, if B ends up being greater than 1, then your application is showing growth. If your base is not equal to, let me erase that. If your base is between 0 and 1, then your application is showing decay. So that remains the same. T is the time elapsed. So it's how long we're going to let whatever the thing is that we have that's growing or decaying, how long we're going to let that do it for. For the most part, for most of these questions, T ends up being your independent variable or your X value. So it's how long the population, the investment, how long it's going to grow for. P is also based in time, but it's not the time elapsed. P represents the time for one period for growth or decay. So, how long does it take to double? How long does it take to triple? And so on. So, P is based in time and will have the same units as T, but it is recognizing how long it takes for one period of growth or decay. So, and one we should also recognize here is Y. Y represents the end amount. So if we have exponential growth, our Y value will be greater than our A value. If we have exponential decay, our Y value will be less than our A value. So Y is the amount that we have at the end of whatever period of time we're letting it grow for. So we're going to use this basic equation. So here's usually the steps that we're going to do for these questions. Your first step often is to write the exponential equation. So take the information given in the problem and write the exponential equation. Fill in that y equals a times b to the t over p. So that's your first step. Write the exponential equation, y equals a times b to the t over p. Okay, now, usually once you have your exponential equation, you need to analyze it, which means either you're going to be given an x value or a t value. You need to determine the corresponding y value. We can either do that algebraically or we can solve for y graphically. So it depends on what kind of question we're given and what the question says. Alternatively, you may have to take your exponential equation that you've created, and then you may be given a y value. Then it is your job to determine the corresponding t value, the corresponding time. Again, we can either do that algebraically, so that's solving algebraically, which we just looked at in the first part of 7.3, or graphically, and we looked at how to do that too. So that's going to be the basic form of all the questions. Create the exponential equation. You may have to take a given x value, determine the y value. You may have to take a given y value and determine the x value or the t value. So let's dive in and do some of these application questions. Here's our first one. Iodine 126 has a half-life of 13 days. So even in this quick little sentence right here, we already know two of our parameters for our exponential function. So part A, write the exponential function that can be used to represent the exponential decay. So y equals a times b to the t over p. And that fraction, that rational, stays in the exponent when we're writing this equation. So for this one, right off the bat, I see half-life. That's our growth rate. Our base is 1/2. It does that every 13 days. There's your p value. So we already know what b and p are. And then reading in part A, write the exponential function that can be used to represent the radioactive decay of 100 grams of iodine 126. That's how much we start with. That's our coefficient or our A value. So our equation then is going to be 100 times 1/2 to the power of t over 13. And the t over 13, all of that is in the exponent. Part B, graph this function using your graphing calculator and state appropriate window settings. So let's get our calculator turned on here. Let's go into y equals and let's put that function in. So 100 times 1/2 to the power of t over 13. So making sure I put that in brackets in this calculator, but that's whole thing is there. Now, before I go ahead and graph it, let's talk about appropriate window settings. The standard window setting here is not necessarily appropriate for this situation. Our X values are going to be representing time. So when I look at the X minimum, there's no use looking at any negative X values. Time can't be negative. So my X minimum is going to be 0. Our X maximum is going to represent the number of days that this substance is going to decay for. Now, I don't know how long we're going to let it decay for, but if we have a look at part C is giving us a value of 50 days. So it might be nice for our graph to go at least as high as 50. So that's what I'm going to set it at. So my X maximum is going to be 50. So I am sort of choosing that randomly. I am letting the question guide me a little bit, but definitely X minimum is 0. And then the X maximum of 50 for now. I can change it if I need to. Our Y value here is representing the amount of the iodine 126 that is left. So our Y minimum is also going to be 0 since we can't have a negative amount of iodine 126 left. And our Y maximum is going to be our initial amount. Because this is exponential decay, we are starting with 100 grams and it's going down from there. So into our window, Y minimum is 0 because we can't have a negative amount of this substance. Y max is 100 because that's our maximum amount. We're going down from 100 grams. We hit graph, and there's our nice exponential decay function, which makes sense since this is a decay question. All right, part C, predict how much. So we want to know Y, the end amount, after 50 days. So I am telling you T is equal to 50. There are 2 ways to solve this problem, and since we're not told a specific strategy to use, we can use one of these 2. The first one would, I guess, be considered algebraic, and that would just be to take the 50 and to substitute into the equation. So take that T is equal to 50, plug it into the equation, and calculate the amount. So if we're going to use our calculator, we're not going to do the graph right now. We're going to go to the calculator part of our calculator, put in our function 100 times 1/2 to the power of, but now where T is, I'm going to substitute 50, then divided by 13. And again, the 50 divided by 13, that whole thing is in the exponent. So we hit enter and we get 6.95. So after 50 days, there is 6.95 grams left. So we'll write that answer down. Y equals 6.95 grams. Alternatively, what we could do is we can use the graph. Because our T is being represented by X, we're given an X value. So what we can do is on the graph, we can just use trace. So I'm going to go back to my calculator. I'm going to go back to the graph that I drew, and I'm just going to hit the trace button, not second trace, just trace. And I'm just going to punch in X is equal to 50, and there's our Y value, 6.95. So this question we can do either way, either by substitution or by graphing, but please make sure you are rounding to the nearest hundredth and make sure that you are writing your units. Part D, describe how you might use your graph to calculate the length of time it will take for 100 grams of iodine 126 to decay to 15 grams. So I am giving you an end amount there. I am giving you a Y value. So Y is equal to 15. So basically what I'm asking you to do is I'm asking you to solve the equation. 15 equals 100 times 1/2 to the T over 13. So we don't know what T is in part D. We know what Y is. So to describe how we want to do this on our calculator, we have to show our steps. So first of all, we would graph the exponential function into y1, which we've already done. Graph the exponential function into y1. We would graph 15 into y2, and then we would determine, we're going to be specific here, the x value of the intersection point. So we are simply solving by graphing. Second part of the question says, how long will it take? So let's actually do it. y1, function's already in there. y2, we're going to put the 15 there. We're going to graph that. So we'll see our exponential decay, and then we'll see our constant function. I can already see where the intersection point is. Second, calculate, number 5 for intersect. Enter, 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 and we're just looking at the x value. Rounded to the nearest tenth would be 35.6. So x equals 35.6, and always write your units. Our time in this case is equal to days. So we can say x equals, or we can say, maybe we'll use t equals since that's the independent variable we're using, and that's how we solve it. So there's our first application question. We use the information from the question to fill in our basic exponential function, and there's our exponential function for this specific question. We took a given x value, found a y value, took a given y value, and found an x value. Let's look at example 4. Whoops. Now, example 4, we're not given the information in words, we're given the information in a table. So what we have to do is interpret the table here in order to create our exponential equation. Here's what's happening. We have a bacteria culture that is monitored starting at 1 p.m. So our starting point is 1 p.m. and the bacteria counts are shown below. Part A, write an exponential equation that represents n at t, the number of bacteria after t hours. So n at t is equal to a times b to the t over p. So n at t just means the same thing as y. We're just using function notation there. So let's look at our table here. And let's look first at what the x values are doing. We start looking at this bacteria culture at 1 o'clock. We record how many we have. So we can see that this is our initial time and our initial amount. So that 250 is very important. That ends up being our A value. It's our initial amount. So let's look at what happens with X. The next time we look is at 4:30, which is 3.5 hours later. After the 4:30 check, we check it at 8, which is also 3.5 hours later. And after the 8 o'clock check, we check it at 11:30, which again is 3.5 hours. So our X is going up by 3.5 every time. In the meantime, our Y values, we go from 250 to 500, 500 to 1,000, 1,000 to 2,000. And hopefully we can see here that this is actually changing by a common ratio, and that common ratio is 2. So our amount is increasing by a factor of 2 every 3.5 hours. We just figured out what our B and P are. So because we're multiplying by 2 over and over and over again, a repeated multiplication means it's exponential, and our base is 2. And because it's multiplying or doubling every 3.5 hours, there's our P value. So our equation for this specific situation is going to be 250 times 2 to the power of t over 3.5. And there's our exponential equation for this one. Part B, algebraically determine, so we have to do this algebraically, the time it takes, so we are looking for t, time it takes for there to be 32,000 bacteria present. So we are given an end amount there. That's our y value, or our t value is 32,000. So the equation that we're looking at then is 32,000 equals 250 times 2 to the t over 3.5. We want to solve for t, which is in the exponent. And we want to do it algebraically. So I can't go ahead and put the function into y1 and this number into y2 and find the intersection point. That's solving graphically. We want to solve algebraically. Step 1, when we solve algebraically, is to get everything into the same base, but we have a bit of a problem. And the 250 is creating the problem. I cannot take 250 and write it as a base of 2. So right now, it's going to be really hard for me to get everything into the same base because of the 250. But here's what we can do. What I'm going to do is I'm going to try to simplify the equation first. So before I try to get everything into the same base, what I'm going to do is isolate the power. So I'm going to divide the right-hand side by 250, which leaves 2 to the power of 3.5 on that side. But if I divide the right side by 250, I have to divide the left side by 250. And on the left side, when we divide 32,000 by 250, we end up with 128. And that actually makes us better off because 128 we can write as a base of 2. So if you're trying to solve algebraically and you can't get everything into the same base, and the equation looks like this, try to simplify. Try to divide by that coefficient, and then maybe that quotient will work out to be a number that you can use. 128 can be written as 2 to the power of 7. And so now we have everything in the same base. We have a single power on both sides and a simplified exponent as well. Since we have that, that means we can equate the exponents. So 7 is equal to t over 3.5. To isolate t, I'm going to multiply both sides by 3.5, and we should get t is equal to 24.5 to the nearest tenth. T in this case is in hours, so we'll make sure we'll write our unit. Our answer is 24.5 hours it will take for there to be 32,000 bacteria. Now, I will not, in this section, you won't be asked to solve algebraically unless you can get everything into the same base. So you may have to do some simplifying, but for this section, if you are told to solve algebraically, you will be able to get both sides into the same base. If you are not able to get both sides into the same base, you'll be told to solve graphically. So there's our second question. We took the information from the table, we created our exponential function, and then we solved it algebraically. Our next equation, or our next application, is based on compound interest. So we need to talk a little bit about what compound interest is first before we can go ahead and do example 5. So first of all, we should recognize that interest is money paid on money. So when you borrow money from the bank says, yes, we're going to lend you that money, but you have to pay us back the money you borrowed plus a little extra. So you pay them for letting them lend you money. Here's how compound interest works. Let's say I borrow $100 and the bank is going to lend me that, but at 10% compounded annually. So every year, my interest is going to compound. What does that mean? Well, let's do some calculations. For the first year, I'm going to take that $100 I'm going to multiply it by 10%, which gives us $10. So I earned $10 in interest. With compound interest, instead of just handing me that money, the bank is going to take that money and is going to add it to my original investment. So for the second year, I have $110. I'm still earning 10% interest. So in that second year, I earn $11 interest. I earn more interest because my investment is bigger. What's the bank going to do? They're going to take that amount and they're going to add it to my original investment. So now I have $121. I'm going to earn 10% on that, which means I get $12.10. The bank is going to take that and add it into my original investment. So look what's happening. My original investment is growing, or my original amount that I borrowed, it is growing. It is compounding. That's what compounding means. When something compounds, it grows. Also, look what's happening here. We have a repeated multiplication. When we have a repeated multiplication, that means that we are talking about exponents. And that's why compound interest is a really good example of an exponential function, because we multiply by the interest rate for every year and we add that interest in. Now, we actually do have a separate compound interest formula. I'm going to show it to you. Oops, it doesn't look like that. But it is exactly the same as our y equals a times b to the t over p, but with something slightly different. So here's what it is. It's a equals p times 1 plus I to the n, but it exactly follows what we've been using, a times b to the t over p. So this is your original amount of your investment, or the original amount that you borrowed. B, now, B is related to the interest rate. But because we want our investment to grow, or because the interest adds to what you owe, we always want our base for these questions to be greater than 1. So when we are given an interest rate, you'll notice that it is 0 decimal all the time. What we want to do is we want to add 1 to our interest rate. That does two things. The first thing it does is it ensures that we are going to have exponential growth. The second thing it does is that's what's actually adding the interest to the initial value. So by going 1 plus I to the n, we are calculating the interest and adding it to the original investment at the same time. And then n is going to be representative of your number of compounding periods. What we're going to have to pay close attention to here is the wording. So we won't always compound annually. If we do, life is good. Compounded annually means once per year. And we don't really have to do any changes to our B value or a P value. However, if we compound more often, so let's say the question says we are compounding semi-annually. That means we are compounding twice per year. That is going to impact your interest rate, and it's going to impact the P value. Your interest rate, which we'll call R for right now, ends up getting divided by 2 because we take the interest rate over the whole year and divide the year in half. Also, your P value, that means that we are compounding every half year. Your P value itself is going to be 1/2, which means we're going to have a compound fraction in our exponent. Sometimes interest is compounded quarterly, which is 4 times per year. That means your interest rate is going to get divided by 4, and it means your P value is 1/4. We may see compounded monthly, which is 12 times per year, which means that interest rate is going to get divided by 12. Your P value is 1/12. So having this fractional P value is going to change the look of our exponent a little bit. Having said all that, let's try example 5. Steve is going to invest $5,800 right away. There's our A value. It's our initial amount. It earns interest at a rate of 6%, 6.7% per year, compounded semi-annually. So very important. That's going to affect our interest rate and our p-value. Part A, write the exponential function that represents the accumulated amount of Steve's investment, A at t, in dollars after t years. So A at t is equal to A times B to the t over p. We've already established that A is 5,800. Let's talk about B. In order to find B, we have to first take that 6.7%, divide it by 100 to convert it to a decimal, so 0.067. And then what we need to do is add 1 to it. And again, the adding of the 1 makes it so it's exponential growth. It also makes it so that it calculates the interest and adds the initial investment at the same time. So our B value is going to be 1.0. Oops, sorry, and I made a mistake. Let's go back a step, sorry. Take that 0.67, divide it by 100. So 6.7 makes 0.067. Then let's divide it by 2. Sorry, that'll be your next step. And the reason we're dividing it by 2 is because it's compounded semi-annually. So this interest rate, which is given over the whole year, gets divided in half because the year is getting divided in half. That's going to give us 0.0335. Now we're going to take that and we're going to add 1 to it. So we have exponential growth. And so the original investment gets added in. So our base is 1.0335. Our p-value, because we are compounding twice per year, that means every half year. So we're going to have t over 1/2. Now that looks pretty messy, having the t over 1/2. So instead of dividing by 1/2, we're going to multiply by 2. So 5,800 times 1.0335 to the power of 2t. So we just took that t divided by 1/2. Instead of dividing by 1/2, we multiply by the reciprocal, and that gives us 2t. There is the equation that is going to calculate the accumulated amount of his investment. How much interest has Steve's investment earned after 12 years? So you're given a t value there. T is equal to 12. Again, we have two choices here. We can either substitute t is equal to 12 into the equation, or we can graph the basic function and then use trace to find and punch in the x value that we're given there. I'm going to do the substitution part. So I'm going to go to the calculator part of my calculator, and we're going to put in 5,800 times 1.0335 to the power of, now it's going to be 2 times 12, which gives us 24. And there we have it. So it's in dollars and cents. Our accumulated amount, A at T, is going to be at $12,790, I think. Yep, and 26 cents. $790.26. Put your dollar sign at the front. Let's quickly show that graphically. When we do it graphically, we graph the basic function, so the function without plugging in the x value, so 5,800 times 1.0335 to the power of, and again use brackets. Here I'm not going to put the 24 in yet or the 12 in yet. Just leave it as the basic function. We're going to graph it. Okay, this one should be exponential growth. We might have to adjust our window a little bit. Yes, we are. So X minimum is going to be 0. X maximum, I don't know that we need 50 years here, but we'll put it there. Our Y minimum, so here our Y minimum is the 5,800. And again, I don't know how high I'm going to go with this, but let's go as high as, let's say, 15,000. And then now there's our exponential function. And so we're going to hit trace and put in the given X value, which is 12. And we should get the same Y value, 12,790 and 26 cents. Okay. Oh, is it 26 or 27? Let's go back here. Oh, yeah, it's going to be 26. So just be careful there of the rounding. Okay, part C. How many complete? Oh, sorry, we're not done part B. This is the accumulated amount. This question asks how much interest has Steve investment earned? So this is the total amount of money he has. To get the amount of interest, what we're going to do is take that total amount and subtract away the initial investment. So that $12,790.26, we're going to subtract away the initial investment to see how much of that is interest. So $6,990.26 is interest. So read the question carefully. If it just asked for the accumulated amount, we would be done up here. But because it's asked for the interest, we have to subtract away the initial investment. Now part C. How many complete compounding periods will it take for the investment to quadruple? So we're actually given a Y value or an A at T value. What we want is we want 5,800 times 4. How long is it going to take to reach that amount? Let's just calculate that really quickly. So 5,800 times 4 is $23,200. So we are given that Y value. We want to know what T value gives us that. So plugging into the equation, we have 23,200, which is equal to 5,800 times 1.0335 to the power of 2t. Now, here's a question that you will not be asked to solve algebraically yet. So in this section, there is no way that I can get everything into a base of 1.0335. So for these investment questions, and we're going to see, for example, 6 down here, where we have these weird bases, you're not going to be asked to solve algebraically in this section. You will always solve graphically. Once we learn logs, so once we move into chapter 8, then we'll be able to solve this algebraically, but currently we can't because the only way we need to solve, we know how to solve, is to get everything into the same base, and we can't do that here. So I'm going to go to the calculator. I'm going to go to y equals. I already have the original function in there. So here I just have to put the 23,200, and I'm going to have to change my window because it's not quite big enough. So I'm going to change my y max to go to 25,000. Graph. There's our growth function. Here's our y value. We need to find that intersection point. Second, calculate number 5, y1, y2, and then enter. We just need the x value. So the x value given is 21. So we should maybe just indicate here, whoops, that we put this side into y2. We put this side into y1, and we found the intersection. And we found that x was equal to 21. Now, we need to be careful. X is representing here, or t, I guess, maybe we should put t. T is equal to 21. T is representing years. So this is saying 21 years to reach to the quadruple. But this question says, how many compounding periods will it take? So this is 21 years. If we have 2 compounding periods per year, we would multiply by 2. So it would take 42 compounding periods. So again, read the question carefully. If it said how many years would it take the investment to quadruple, we would say 21. Because it asks how many compounding periods, and because we are compounding semi-annually, we multiply our years by 2. Example 6. In example 6, this is a question where we're looking at depreciation of the value of an item. And in this case, we're actually given the exponential function. A car was purchased in January of 2015, and its value can be modeled by the function V equals 45,000 times 0.915 to the power of t, where t is the number of years since the car was purchased. Part A, explain what each value in the function represents. Okay, so we need to be very specific about what we're saying here. So let's start with the 45,000. So 45,000 is our A value, but that doesn't really explain what it is. We know that the A value represents the initial value, but that's also not quite specific enough. We want to say that 45,000 is the initial value of the car, or we could also say it is the price of the car when purchased. But we need to be specific. We need to answer in the context of the question. So just saying it's the A value or just saying it's the initial amount is not enough. We have to say that it's the initial value of the car, the value of the car when we purchased it. The other value in the equation is 0.915, and we know that that is our growth rate or our base, but that's again not specific enough. What I notice first of all is that because that B value is less than 1, I recognize that it is going to be the rate of decay. But that also is not specific enough. So it's the rate of decay of the value of the car. And again, not quite specific enough. What is that rate? So here's where we need to be really, really careful with our base and stating the rate of decay. Our base is 0.915. That does not mean that the price of the car is decaying by 91.5%. That wouldn't make sense. In order to figure out what our actual rate of decay is, what we're going to do is we are going to take that B value, subtract it from 1, so 0.1 minus 0.915, and then we're going to take that and multiply it by 100. What that ends up giving us is it ends up giving us 8.5%. So our rate of decay is 8.5%. And because it is in years, we also need to specify that it's 8.5% per year. So we can't just say it's the growth rate or decay rate. We have to say what is decaying. We have to say by how much and how often. So being very, very specific to the words in or the context of the problem. Now, this is a rate of decay. Keep in mind that if we had a growth rate, that we would determine that rate a little bit differently. So let's say, for example, we had something and the base was 1.075. Then we would do a similar thing, but we would subtract 1 and then multiply by 100. So in this case, the growth rate would be 7.5%. So just pay attention to your B value and recognize that you're going to have to go from the B value to either the rate of decay or depreciation, or if a B value is greater than 1, we'll have to find the rate of appreciation or growth. So that's part A. Explain what each value represents. going back to the context of the problem every time. Part B, evaluate the car's worth after 18 years. We are given a T value, and again, we have two choices. We can either substitute into the given equation, or we can graph the given equation and use trace to find the y value that we're looking for there. Now, keep in mind that this is the equation we're using. So even though the rate is 8.5%, this is what's calculating our value. So this is the equation that we're going to use. I'm going to do the substitution first. So again, just in the calculator part of the calculator, I'm going to put in 45,000 times 0.915 to the power of, and then I'm going to substitute in the given x value, which is 18. So after 18 years, the value of the car is $9,094, and I think I saw 78 cents there. Yeah, and 78 cents. So that's the value of the car after 18 years right there. So that would be your y value. I'll show you that graphically as well. When we solve by graphing, we are going to graph the original function. So we're not going to put the 18 in yet. We're going to graph the function 45,000 times 0.915 to the power of x. Okay, let's check our window settings. So are we going to have this car for 50 years? Probably not, but I'm just going to leave it at 50 right now. Your y minimum is 0. The car cannot have negative value. And then the maximum value is our initial value, which is the 45,000. We should have a lovely decay function. There it is. Because we're given an x value, we're going to hit trace and just type in that x value of 18, the y value $9,094.78. Question C, determine the year. So with a time, we're looking for t, in which the car will be worth half its original value. So what we are doing is we are taking the original value and dividing it by 2, and that is a y value. So let's just check what that value is. 45,000 divided by 2 is going to be 22,500. There's our given y value. We need to find our x value. So here's what we have as an equation. And again, because we have kind of a weird base, we are not going to solve that algebraically. We're going to solve it graphically. I already have this function typed into y1. So I'm going to put this y value into y2, and we are going to find the intersection point. We are only interested in the x value of that intersection point. So into y equals, function's already there. Just going to put the 22,500 into y2. We can see the intersection point pops up right away. y1, y2, and guess. And we get t equals, or x equals, I didn't even look at it. Where is it? There we go, 7.8. We're going to say to the nearest tenth right now. So that would be 7.8 years. Let's be careful though, and let's look at the question. It says determine the year in which the car would be worth. So because we start in January of 2015 and we go for not quite 8 years, we're not going to round this. We go for not quite 8 years. This would be in 2022. So be careful how you answer that question. We are starting in January of 2015, so at the beginning of the year, we're going for not quite 8 years. If I said 2023, it doesn't happen in 2023. That would mean that it took more than 8 years. It doesn't quite take 8, so 2022. So there are some examples of um, applications of exponential functions. You have the job of creating the exponential function. You have the job of finding a y value either by substituting or tracing on the graph. And then you also have the job of solving either algebraically, if we can get both sides into the same base, or graphically if we can't. Here are some questions for you to practice.